The Higgs boson, often called the God particle, was discovered in 2012, confirming the existence of the Higgs field and completing the standard model of particle physics. But here's the shocking part: according to our current understanding, the Higgs boson shouldn't exist. Its mass is too perfect, too delicate, teetering on the edge of stability. If our theories were completely right, the universe should have collapsed moments after the Big Bang. So, what's going on? Did we miss something fundamental? Today, we're diving deep into why the Higgs boson's existence creates a massive crisis in physics. The Higgs boson was predicted long before its discovery at CERN's Large Hadron Collider. When it was finally detected, scientists measured its mass at around 125 giga-electronvolts, GeV. This value is shockingly fine-tuned, too perfect to be a coincidence. Why is this a problem? Because, according to quantum field theory, the Higgs boson's mass should be affected by interactions with every other particle in existence. The calculations suggest it should be much heavier, around a quadrillion times larger. Yet, the value we observe is much lower, implying that something unknown is counteracting these effects. Physicists call this the hierarchy problem. Without a deeper explanation, the Higgs boson's mass is an unsolved mystery, leaving us questioning the very fabric of our reality. Here's where things get even crazier. The Higgs boson plays a crucial role in determining the stability of our universe. The equations of the standard model suggest that the Higgs field exists in a delicate, metastable state, like a ball balanced on the edge of a hill. If even a tiny quantum fluctuation were to push it past a critical point, the universe could transition to a lower energy state, causing catastrophic decay at the speed of light. According to calculations, the Higgs boson's observed mass places us dangerously close to this boundary. Theoretically, the universe shouldn't have lasted this long. Some scientists suggest that unknown physics, perhaps related to dark matter or new fundamental forces, might be secretly stabilizing our universe. But as of now, we have no idea why the Higgs hasn't already triggered cosmic destruction. One proposed solution to this crisis is supersymmetry, SUS, a theoretical framework that suggests every known particle has a heavier twin. If supersymmetry is real, these partner particles could cancel out the quantum effects, pushing the Higgs boson's mass to insane values. The problem? We haven't found any of these particles. Despite years of searching at the LHC, no evidence for supersymmetry has emerged. This has left physicists scrambling for alternatives, as the simplest SUSUY models seem increasingly unlikely. If supersymmetry isn't the answer, we may need an entirely new paradigm to explain the Higgs boson's bafflingly low mass. Some physicists believe that the only way to explain the Higgs boson's fine-tuned mass is to consider the multiverse hypothesis. This idea suggests that countless universes exist, each with different physical constants. In most of them, the Higgs boson would be too heavy, leading to a dead, lifeless universe. But in rare cases like our own, the Higgs just happens to have a mass that allows for stars, planets, and life to exist. While this idea is fascinating, it's also deeply unsatisfying to many scientists. The multiverse is impossible to test with our current technology. If we can't confirm its existence, then it's not really science, it's philosophy. The Higgs boson has exposed cracks in the foundation of modern physics. The standard model, despite its success, cannot explain the Higgs mass problem, dark matter, or gravity. This means new physics must exist, we just haven't found it yet. Future experiments at the LHC and proposed next-generation colliders could provide crucial insights. Scientists are searching for new particles, hidden forces, and potential quantum gravity effects that might explain the Higgs boson's strange behavior. Whatever the answer is, one thing is certain: we are on the brink of a major scientific revolution. One of the biggest challenges in explaining the Higgs boson's mass comes from quantum corrections. In quantum mechanics, particles don't just exist as single entities, they constantly interact with virtual particles that pop in and out of existence. These interactions add energy to the Higgs boson, making it seem like it should be far heavier than what we observe. If quantum corrections were left unchecked, the Higgs boson's mass should naturally rise to extreme values, possibly near the Planck scale far beyond the range of known physics. Yet somehow, it remains at 125 GeV. This implies that some unknown mechanism is delicately balancing the quantum effects, keeping the Higgs mass unnaturally small. Scientists call this the fine-tuning problem, and solving it may require a completely new understanding of nature's fundamental forces. Some theories suggest that hidden extra dimensions might be influencing the Higgs boson. In string theory, for example, additional spatial dimensions exist beyond the familiar 3 of space and 1 of time. These extra dimensions could provide a natural explanation for why the Higgs mass appears so finely tuned. One possibility is that gravity leaks into these extra dimensions, weakening its effect on the Higgs boson. If true, this could explain why the Higgs hasn't collapsed under its own quantum corrections. However, detecting extra dimensions remains one of the biggest challenges in physics, as they are theorized to be incredibly small and hidden from direct observation. When the LHC discovered the Higgs boson in 2012, it was a groundbreaking moment in physics. But the machine's work is far from over. Physicists are now using it to probe the Higgs boson more deeply, looking for clues that could explain its stability. One key focus is measuring how the Higgs interacts with other particles. If its interactions deviate even slightly from standard model predictions, it could hint at new physics beyond our current understanding. Scientists are also searching for rare Higgs decay processes that might reveal hidden forces or unknown particles affecting its behavior. Dark matter makes up about 85% of the universe's mass, yet we still don't know what it is. Some theories propose that the Higgs boson might interact with dark matter particles in ways we haven't yet detected. If dark matter particles exist, they could subtly influence the Higgs field, providing a natural explanation for why the Higgs boson has such a peculiar mass. Some experiments are testing whether the Higgs boson can decay into dark matter particles, but so far, no evidence has been found. If such interactions exist, they could be the key to unlocking one of the greatest mysteries in physics. Imagine a universe where the Higgs boson had a slightly different mass. Even small changes could have catastrophic consequences for the existence of atoms, molecules, and life itself. If the Higgs were heavier, the fundamental forces governing particle interactions would be different, possibly preventing atoms from forming. If it were lighter, the early universe might have expanded too rapidly, preventing galaxies from ever forming. This delicate balance suggests that something beyond the standard model is fine-tuning the Higgs boson's properties, whether it's new physics, hidden symmetries, or even something as radical as intelligent design in the laws of nature. One of the most perplexing questions in physics is why gravity is so much weaker than the other fundamental forces. If we compare the strength of gravity to the electromagnetic force, it's about 10 times weaker, an almost incomprehensible difference. The Higgs boson's mass is at the heart of this puzzle. If the Higgs were much heavier, it could provide a natural explanation for why gravity is weak. However, since it remains at an unnaturally low value, physicists are left wondering if an unknown force or principle is suppressing its mass. Some suggest that hidden symmetries in nature, or even entirely new particles, may be responsible for this fine-tuning. What if the Higgs boson's perfect mass isn't a coincidence, but rather a requirement for our existence? This is where the anthropic principle comes in, a controversial idea, suggesting that the universe appears fine-tuned simply because if it weren't, we wouldn't be here to observe it. According to this view, there may be countless universes with different physical laws, and we just happen to be in the one where the Higgs mass allows for atoms, chemistry, and life to exist. While this idea is intriguing, it's difficult to test scientifically, making it more of a philosophical question than a physical theory. One way to test for new physics is by looking at how the Higgs boson decays. In the standard model, the Higgs should decay into familiar particles like quarks, W and Z bosons, and photons. However, if it decays into unknown particles, it could hint at new forces or undiscovered particles. Scientists are particularly interested in whether the Higgs boson decays into invisible particles, which could be a sign of dark matter interactions. While no clear evidence has been found yet, future experiments may reveal if the Higgs boson is secretly hiding new physics. Most physicists assume the Higgs boson is a fundamental particle, meaning it isn't made of anything smaller. But what if that assumption is wrong? Some alternative theories suggest that the Higgs boson could be a composite particle made up of even more fundamental components. This idea is similar to how protons and neutrons were once thought to be indivisible until scientists discovered they were made of quarks. If the Higgs is composite, then it might explain its unexpectedly low mass. However, proving this theory would require detecting signs of Higgs substructure, something current experiments haven't been able to do yet. The Higgs field played a critical role in shaping the early universe, but could it have done even more? Some physicists believe that the Higgs boson could be connected to the mysterious inflationary period that occurred just after the Big Bang. Inflation was a brief moment of rapid expansion, where the universe grew exponentially in a fraction of a second. Some models suggest that a Higgs-like field might have triggered this event. If true, studying the Higgs in detail could help us understand what caused the Big Bang itself, one of the biggest mysteries in cosmology. One of the most unsettling implications of the Higgs boson is its connection to the ultimate fate of the universe. If the Higgs field is metastable, then in theory, a quantum fluctuation could trigger vacuum decay, collapsing space-time into a lower energy state and destroying everything in existence. While this scenario is terrifying, current calculations suggest that if vacuum decay happens, it would likely occur trillions of years from now, long after our sun and galaxy have disappeared. Even so, this possibility raises profound questions about whether our universe is truly stable, or if we are living on borrowed time. Many theories predicting new physics, like supersymmetry, suggest that the Higgs boson should have a partner particle. This partner would help cancel out the quantum corrections that should have made the Higgs mass enormous. However, no such particle has been found at the LHC. The absence of a Higgs partner is a major challenge for supersymmetry. If such a particle exists, it must be heavier or harder to detect than originally thought. Some physicists worry that we may need a much more powerful collider to find evidence of these hidden particles. The Large Hadron Collider has given us incredible discoveries, but it may not be enough to answer the Higgs boson's biggest mysteries. That's why scientists are proposing the Future Circular Collider, FC, see a machine 4 times larger than the LHC capable of smashing particles at much higher energies. If built, the FCC could provide the most precise measurements of the Higgs boson yet, helping to determine whether unknown forces are acting on it. Other proposed colliders, like a muon collider, could provide even more detailed insights into the Higgs and the physics beyond the standard model. The discovery of the Higgs boson was a major victory for physics, but it also opened new doors to deeper mysteries. The very fact that the Higgs shouldn't exist in its current form suggests that something profound is missing from our theories. As we push the boundaries of science, new experiments and technologies will bring us closer to the truth. Whether it's through high-energy colliders, quantum gravity research, or unexpected discoveries, the Higgs boson may ultimately be the key to unlocking the next great revolution in physics. One of the greatest puzzles in physics is why the universe is made mostly of matter and not an equal mix of matter and antimatter. According to the standard model, the Big Bang should have created equal amounts of both, causing them to annihilate and leave behind an empty, lifeless universe. Some theories suggest the Higgs boson might have played a role in this imbalance. If the Higgs field interacted differently with matter and antimatter in the early universe, it could have tilted the scales in favor of matter. This idea is still unproven, but future experiments may reveal whether the Higgs is the missing link in solving the matter-antimatter mystery. In the standard model, there is only one Higgs boson, but some extensions of the theory suggest that multiple Higgs-like particles could exist, each with different properties. For example, the 2 Higgs doublet model, 2HDM, proposes that there are at least 5 Higgs particles, some of which could interact differently with dark matter or new forces. If one of these additional Higgs bosons is discovered, it would be a clear sign of physics beyond the standard model, completely reshaping our understanding of fundamental forces. The Higgs boson is crucial to explaining the weak nuclear force, which governs radioactive decay and nuclear reactions in stars. The Higgs field is responsible for giving mass to the double U and Z bosons, the particles that mediate the weak force. However, some physicists believe that the weak force might have an undiscovered connection to another fundamental force. If the Higgs boson has additional interactions beyond what we currently observe, it could point to a hidden fifth force of nature, which could explain unresolved mysteries in physics. The Higgs boson might also have unexpected implications for the field of quantum computing. Since the Higgs field interacts with fundamental particles at the quantum level, some researchers wonder if understanding these interactions could lead to new ways to manipulate quantum information. If future studies uncover hidden quantum effects related to the Higgs field, they could lead to breakthroughs in quantum cryptography, computing power, and secure communication, pushing technology into an entirely new era. Some experimental results related to the Higgs boson have shown tiny deviations from standard model predictions. While these deviations are small, they could be the first hints of a deeper theory waiting to be uncovered. Physicists are carefully analyzing Higgs data to look for signs of new physics, such as interactions with unknown particles or hidden symmetries. If confirmed, these anomalies could provide clues that lead us toward a theory of everything, a unified framework explaining all known forces of nature, including gravity. The Higgs boson is often credited with giving mass to particles, but this is only partially true. While it explains why fundamental particles like quarks and electrons have mass, it does not explain the mass of protons and neutrons, which make up most of the visible universe. In fact, only about 1% of your body's mass comes from the Higgs mechanism. The remaining 99% comes from the energy of quarks and gluons inside protons and neutrons, as described by quantum chromodynamics, QCD. This means that while the Higgs is important, it is not the full answer to the origin of mass, leaving yet another mystery for physicists to solve. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.